Hello. Can we resume?
Yeah, sure. I think everyone is here.
Okay, let's do it. Okay, so now we already have given the proof of the converse of the theorem, and now we talk about the achievability of the channel capacity, meaning that for any rate we transmit which is below channel capacity C, then as the number of as n, which is the block length of the code grows, we eventually we would be able to achieve reliable communication. Okay, how to prove achievability? So we consider this DMC specified by the transition matrix transition probability Py equal X. And so the plan is that for every input distribution Px, we want to prove that's the rate Ixy, which is the mutual information between X and Y, the input and output, is achievable by showing that for large N, there exists a channel code such that the rate is the code is arbitrarily close to the mutual information, and the maximal probability of error, lambda max, is arbitrarily small. And then we choose the input distribution Px to be the one that achieves the channel capacity, that is Ixy is equal to C. Okay, so we need a this lemma, which is essential in the argument. So now the idea is the following. So let me instead of going through this this mess, I'll draw you a picture. Okay, so so we have a X sequence and Y sequence. Okay, so if for each one of them I draw it according to Pxy, okay, then when n is large, when is the so this x1 and y1 is xn yn. Okay? If n is large, then by the joint AEP, the probability that x y being jointly typical would tends to 1. Okay? So with very high probability, then the two sequences x and y that are obtained are jointly typical would be very close to 1. Now, however, instead of using the this joint distribution Pxy for each one of them, I use the product distribution. The product distribution means that I keep the marginal, not marginal distribution, but I make this x1 and x1 and y1 independent of each other. The same thing for every pair of these random variables. Now, if I do it this way, this lemma says that the and I call this instead of xy, and now I call this I call this x prime and y prime, okay, being generated in this fashion. This lemma says that the probability that x prime, y prime together form a pair, which is jointly typical, is at most given by this 2 to the power n minus n times the mutual information minus some small quantity tau, where tau tends to 0 as delta tends to 0. So essentially, the probability that X prime Y prime pair forms a jointly typical pair it decreases exponentially fast, and where the exponent is equal to the mutual information between X and Y. Now, instead of giving you a formal proof, I would like to give you the intuition behind it. Okay, so the interpretation of this lemma is the following. Now, it's very much like this. We randomly choose a row with a uniform distribution, a row here. Okay, remember this this joint typicality array. So the rows are each one of them is a typical X sequence, and each column denotes a typical Y sequence. Okay, so if you draw a so this X prime and this Y prime. Okay, now drawing this X prime is very similar to randomly drawing a row by the EP. Okay, it's without equipartition property, because most likely you obtain a typical sequence for X prime, and the set of typical sequences has an almost uniform distribution. So the situation is very much like you uniformly draw a row, and then you uniformly pick a column for this Y prime, and you ask what is the probability that they are jointly typical, namely that the intersection of the row and the intersection of the column actually has a dot in it. Now, so the roughly speaking is like this: the probability that you obtain a jointly typical pair is equal to the number of dots, okay, number of dots divided by the number of row and column pair, which is to the power n times entropy of X times to the power n times entropy of Y. Okay, so if you work this out, you'll find that it's equal to 2 to the power n times entropy of xy minus entropy of x minus entropy of y, right? Which is equal to 2 to the power minus entropy of the mutual information between x and y. So this is the intuition. Okay. Okay, so this is an informal proof of this lemma. So I'm going to skip the formal proof. Okay, so I'm going to describe to you something called random coding scheme. In a random coding scheme, we generate a code in a random fashion, and we're going to analyze the performance of this code on average. Okay, so here the first thing is about parameter settings. So we set let epsilon be a small quantity, which is fixed it to be a small quantity, and we fix an input distribution. So remember that we want to find the input distribution that maximizes the mutual information between the input and output. But let's say we just pick any arbitrary input distribution and fix it for the time being. And we let delta to be a small quantity to be specified later. And we let m, the m is the size of the message set, okay? We let m be an even integer, satisfying this, this inequality. So on the one hand, it is greater than the mutual information minus epsilon over 2. On the other hand, is less than the mutual information minus epsilon over 4. Okay. Now we don't want it to we want to be close. We want, this is 1 of n times log m is the rate of the code. We want the rate of the code not to exceed IXY. Okay, so it is less than IXY minus epsilon over 4. At the same time, we want it to be close to IXY, so it is larger than IXY minus epsilon over 2. Okay. Now, if if the rate is approximately equal to IXY, it means that the number of messages that you can choose from is approximately equal to 2 to the power n times the mutual information between x and y. That is, the number of messages grows exponentially with the rate at the rate IXY. Okay, here's the random coding scheme. So we construct the code book, we construct an NM code randomly by generating M code words independently and identically according to px to the power n, meaning the following. So we want to generate M code words, each one of length n, and we fill each of these cells according to the distribution px, which is the input distribution that we choose. So we do it in an IID fashion, and we fill out all these cells, and then we review. This is a code book that we're going to use. It's a random code book, okay. But once it's a random code book, but once you draw the code book, you fix it, right? And then you review the code book C to both the encoder and the decoder. And then a message W is chosen from the message set according to the uniform distribution. And then we transmit the corresponding code word through the channel, and we denote this by x tilde of W. X tilde of W is the Wth code word. So the first code word is x tilde 1, the second one is x tilde 2, the last one is x tilde m, and x tilde W is the Wth code word that you have generated. And then the channel outputs sequence Y according to the transition probabilities, like this. So it takes the product form. Okay, and then the sequence Y is decoded to a particular message small w if the code word associated with the Wth message and the received vector Y is jointly typical, and there does not exist another code word in the same code book which is jointly typical with that output sequence Y. So what you do for decoding is that you look. So I receive a vector Y, okay, from the channel, and then I look over my code book. I look into every code word, and I check whether the first code word is and Y are joint typical or not. Okay, I just check out every code word. If it happens that you can only find one code word which is jointly typical with the Y, and one and only one. Okay, if then you decode, if it happens to be W hat of W, which is the code word which is the unique code word jointly typical with the Y sequence, then you decode the message to the message W. Okay. In other words, if this fails, then I'm sorry. Okay, if this fails, then then you declare a decoding error. Okay. All right. So the situation that you would decode you declare a decoding error is the following. It could be that you cannot find any of the code word which is jointly typical with the Y, or you find more than one code word that are jointly typical with the Y. In this situation, you declare a decoding error, and then and what you do is that you decode y to a constant message in the message set. Okay, so you just arbitrarily pick a constant message. Whenever there's a decoding error, you decode to that message. Okay, but actually, I shouldn't call it decoding error. You just map it to a constant message. So you don't explicitly tell you don't explicitly declare a decoding error. So now we want to show that the probability of error, that is the probability that you don't decode correctly, can be made arbitrarily small. Now we consider the so instead of going through this, I just want to mention that the probability of error is actually equal to the probability of error given that you send out the first code word. This is by symmetry of the problem, because you draw the code words in exactly the same fashion. So the probability of error is without loss of generality, we can assume that we have sent out the first code word. That is the message. The value of the message is equal to 1. Okay, or the first message is chosen. So this is the situation. So we send the so the box on the left hand side is the code book, which consists of m code words, and then we send the first one through, and through the channel we obtain the output sequence y. And then now we define an event associated with a message w. Okay, so this event is denoted by E sub w, and it is the condition. It is the situation that the w's code word is jointly typical with the y sequence that you receive after the transmission. Now, if E1 occurs, that is the first code word is jointly typical with the y, but the EW does not occur for any other w from 2 to m, then we can then there's no decoding error, because the first code word is the only code word that is jointly typical with y, and according to our decoding rule, we will decode to the first message. And this is correct, because we assume that the first message was the message being chosen. So therefore, the probability of not having an error, okay, conditioning on w equals 1, is equal to is greater than or equal to the intersection of these events. Okay, the intersection of these events is precisely what is being highlighted here. So E1 occurs, and E2 does not occur, E3 does not occur, so on and so forth. EM also does not occur, because this event implies there's no error. Okay, this probability is less than or equal to this probability. Okay, now we consider the probability of error. So the probability of not having error conditioning on w equals 1 is lower bounded by this, and now we consider this. Okay. The probability of error given w equals 1 is equal to 1 minus the probability of no error conditioning on w equals 1. Okay, and then according to this this lower bound, we have this. This becomes an upper bound because there's a negative sign there, and it's upper bounded by this, and using the De Morgan's law. Okay, so this is E1 intersect E2 complement, so on and so forth. In the next line, I just apply De Morgan's law and write this as the complement of E1 and E2 complement. Let's see. Oh, that's a let's see. Oh, okay. Because it's just one minus the probability. It's one minus the probability of this event, so it is equal to the complement of this event. Okay, so it's just the complement of the this is just the complement of this event. Okay? Just take the complement, and then we okay, it's fine. Okay, and then I apply in next line I apply De Morgan's law, and so the intersection of these events is equal to the union of the complements of these events. So this becomes E1 complement union E2 complement, so on and so forth, and the last term is EM. Right? So and then by the so what it boils down to is that if you have an error, okay, it means that either E1 it implies that either E1 complement is true, that is the first covert is not typical with the Y, or the second covert is typical with Y, and third covert is typical with Y, so on and so forth. Okay. Now by the union bound, so we're going to so this is I'm sorry that it blocks the screen, but here the last line here is the probability of the union of events. So what we do is to apply the union bound so that we can write the probability of error given W equals 1 is less than or equal to the sum of all these probabilities in the union. So the first term is probability of E1 complement given W1, W equals 1, plus all the other terms from starting from 2, it is probability of EW given W equals 1. Now, the E1 complement means that the first covert is not typical with the Y. Now this happens with very small probability by the joint AEP, because x1 to the 1 is drawn according to px, and then we pass it through the channel py given x. Okay, so that the so it is exactly like drawing a pair according to pxy n times. Okay, so according to the joint AEP, the probability that this covert is joint typical with the Y has very high probability. So so that the for the first term, okay, this term actually it is the case that they are not joint typical. Right? The probability is very small. Using strong joint EP for sufficiently large n, this would be less than any small quantity nu. And the so we have treated this case. Now the so for how about for each of these probabilities in the summation, this is the probability that another. So this is the one that's being transmitted and received the Y, and this is the probability that let's say W is equal to 2. This is the probability that W2 hat is jointly typical with the Y. Okay. Now this is if you look at just for example x2 hat is according to x2 hat is according to oops, sorry, px to the power n, right? And y, this y has a distribution py to the power n. It's a marginal distribution. However, this vector and this vector are independent of each other. Okay, they have the same marginal distribution as x being drawn n times, and this is the marginal distribution as y being drawn n times. Then according to our lemma, the probability that this sequences and this sequence are jointly typical with each other would be less than, okay, let me remove this. Okay, so we look at the situation that this sequence is any one of these sequences in green are jointly typical with the output vector y, and and for each of these w's from 2 to m, according to this lemma that we have we just talked about, okay, the probability that this one is and this one are jointly typical is less than or equal to 2 to the power minus n times the mutual information minus some small quantity tau. Okay, so like this, and then well, we know that we choose the rate such that it is close to IXY, but not quite. Okay, and at any rate, so this translates to m is less than 2 to the power n times IXY minus epsilon over 4. Okay, so the rate of growth, the exponential rate is of growth is the mutual information minus a small quantity. So we have to keep the rate strictly less than the mutual information in order for things to work. So therefore the so here we have this so we're coming back to here. Okay, so whether you have the conditioning on w equals 1 or not, it doesn't matter by symmetry. So we're following this line, the probability of error, like here, is less than or equal to the first term. The first term is upper bounded by gamma, okay, by strong joint AEP, and the term here, each of these terms is less than or equal to 2 to the power minus n times entropy minus tau, which is this one here, okay, and the okay, so actually I have done the animation here, and then for this one, it's upper bounded by this, okay, and then the w is from 2 to m, so the total number of terms here is less than m, where m is less than 2 to the power n times the mutual information minus epsilon over 4, according to our assumption. Okay, so we have this, and then we find that we can cancel out the mutual information, and so we end up having this. The probability of error is upper bounded by nu, which is any number you can choose, plus 2 to the power minus n times epsilon over 4 minus tau. Now, recall that epsilon is fixed, so this epsilon is fixed, and this tau goes to 0 as delta goes to 0. Okay, so we can actually choose a delta is specifies the is the parameter we specify the typical set, okay, Tn x y delta. So this is this delta, okay, where you define the typical set. So we can choose the delta to be sufficiently small so that the epsilon over 4 minus tau is greater than 0. Right? So the so if you choose delta to be smaller than tau, can also be small. So at one point, tau would be strictly smaller than epsilon over 4, so that we can make this term strictly positive. If this thing in the bracket is strictly positive, 2 to the power minus n times this bracket would tends to 0 as n goes to infinity. Okay, So by letting, we first let delta to be small so that the bracket becomes strictly positive. And then we let n goes to infinity to make this as small as we want. And finally, we can choose nu to be less than epsilon over 3. And we choose this to be less than epsilon over 3. And then we choose n to be large enough so that this is less than or equal to less than epsilon over 6. So at the end, we can make the probability of error less than epsilon over 2 for any epsilon that you can fix at the beginning, as long as you choose a sufficiently large n. So the idea is that the smaller you choose epsilon, that the larger you will need n to be. Okay, so this is the performance of the random code, which means that if you construct a code randomly and you use the code as I have described to you, then the average probability of error averaging over all the code books would be less than or equal to epsilon over 2. Then you would ask, hey, Professor Yeung, but this does not really show the existence of a good code, but actually it does. The idea of the analysis is the following. Okay, okay, before I get into that part, let me recap what we have done. So we let n to be large, the block length to be large, and then we by joining AEP, you assume that you transmit the first code word. Then the first code word being jointly typical with y would have a probability being very close to 1 when n is large. And then for the other code words that you didn't transmit, the probability that for that particular code word to be jointly typical with the received vector y is approximately equal to 2 to the power minus n times the mutual information. Okay, now when C, which is the size of the code book, M, okay, the size of the code book grows at a rate less than IXY, then the probability that the Wth code word being jointly typical with Y, okay, for some W not equal to 1, can be made arbitrarily small. Okay. As the key is that the rate of the code cannot grow at a rate higher than IXY. Okay, if the rate of the code grows at a rate higher than IXY, then you cannot make sure that this probability happens with an arbitrarily small value. Okay, so under these two conditions, so this is important. You need to make sure that the rate of the code does not grow at a rate higher than the mutual information. Under this situation, then we can make the probability of error arbitrarily small. Okay, now how about the existence of a deterministic code? So so according to the random coding scheme, the probability of error is actually the probability of error for any particular code that you can choose by this random scheme, and then you average over all the code books. So this means that there exists at least one code book C star such that the probability of error of that particular code book C star is less than or equal to epsilon over 2. The reason is that it's very much like I have a set of numbers where the average is equal to 10. Okay, then there must exist one number which is less than or equal to 10. Okay, so it's just like that. So if the let me rephrase it. So I have a set of numbers where the average is less than or equal to 10. Then one of the numbers must there must exist at least one number such that the number is less than or equal to 10. If otherwise, then it's not possible that the average of the numbers is less than or equal to 10. So that's the idea. So this shows the existence of at least one codebook C star that can do the job. Okay, now by construction, now this codebook has rate larger than IXY minus epsilon over 2, right? So this is how we choose the rate to start with. Now there's a small thing that we need to fix regarding the lambda max and PE. Okay, so we have shown that there exists a codebook such that the average probability of error is less than or equal to epsilon over 2. But we want, according to our definition of achievability, we want a codebook with a lambda max less than epsilon. That is, the worst codeword has a probability of error less than epsilon. So this is not quite what we want yet, but we are actually getting very close. So instead of giving you a formal proof, I'll just describe to you the procedure of obtaining the desired code. All right. So what we do is that so we have a codebook such that PE, the average probability of error, is less than epsilon over 2. And so what we do is that we order the codewords according to the conditional probability of error. So without loss of generality, we assume that the first codeword is the best, and then the second codeword, so on and so forth. So it has a decreasing conditional probability of error. So it turns out that by taking the better half of the codebook, okay, namely that I divide the codebook into two halves. The right hand side is the worst half, and the left hand side is the better half. By discarding the worst half of the codebook, then I can guarantee that the worst codeword in the better half has the conditional probability of error less than epsilon. Okay, so I'm originally I have epsilon over 2, but by the average of these things is less than epsilon over 2. But by discarding the worst half, I actually can guarantee that the worst codeword in the better half has conditional probability of error less than epsilon. Now, by doing this, I actually sacrifice the coding rate because I chop off the half of the codewords. Okay. But actually, this does not matter asymptotically because the rate originally is 1 over m times m, but now we have 1 over m times log m over 2 because we just chop off half the codewords. And however, you're just losing a factor of 2, but if you divide things by n, you take the logarithm and then divide things by n, it's not going to make any difference asymptotically. So you lose only an arbitrary small amount of the rate when n goes to infinity. So that's the main idea. Now, okay, so in the interest of time, I will stop here for the very technical part of the discussion, but I would like to say a few words about the intuition behind the channel coding theorem, which I think would be more important for many of you. Okay, so now the channel coding theorem says that it says something much stronger than that the bit error rate tends to 0. It actually says that for an indefinitely long message, an indefinitely long message can be communicated reliably through the channel when the block length n tends to infinity. So when you decode correctly, I mean that you can decode a message correctly. That doesn't mean that I can decode. If you think of the message having many bits, I am not saying that you can decode every bit with high probability. Because if you decode every bit with high probability, if you have many bits, then if one bit is not decoded correctly, then the whole message is screwed up, right? So the channel coding theorem actually asserts a very strong notion of reliability. And the direct part of the channel coding theorem is called an existence proof as opposed to a constructive proof, because it only tells you that there exists a code, but to find out which one, it takes an exhaustive search, which is not very feasible most of the time. And so a randomly constructed code has the following issues. Encoding and decoding are computationally prohibitive, and very high storage requirement for the encoder and decoder. And nevertheless, the direct part implies that when n is large, if the code words are chosen randomly, most likely the code is good, although it's not very practical, but it's good code. And it gives much insight into what a good code would look like. So going back to our original discussion, we first look at the repetition code, which is a code which can achieve high reliability, but the coding rate tends to 0, which is very bad. Okay, and now we learn about the channel coding theorem, and we know what a good code would look like for a BSC, for a binary symmetric channel like this one. Okay, the maximizing distribution is one which is uniform, right? Which means that for a good code, most of the code word would have half zeros and half ones, and that's why from this point of view we see that the repetition code actually is not a good code, because in the repetition code it has only 2 code words. One consists of all zeros and the other one consists of all ones. That's so now we see that this is not an indication of the code being a good one. Okay, and another intuition that I would like to bring up is the following. Now on the left hand side, you imagine that each one of these is a code word which is a typical sequence. Okay, you transmit the typical sequence through the channel py given x. Then by the conditional strong EEP, it would be most likely would be one of these 2 to the power n times entropy y given x y sequences. Okay, and so this one can become one of these things, and this one can become one of these. Now, in order for decoding to be possible, you think of this as being a cone. Okay, in order for decoding to be possible, these cones got to be non-overlapping, and the number of typical sequences is approximately 2 to the power n times entropy of y, and the size of each of these cones is 2 to the power n times entropy of y given x. So if you divide this by this, you get this, okay, which is hy minus hy given x is equal to 2 to the power n times entropy 2 to the power n times the mutual information between x and y. And when you choose the maximizing input distribution, then you get NC. So that's why the number of cores cannot exceed this value. Right? So okay, and there is another discipline which is closely related to information theory called channel coding theory. As I mentioned, random coding or random code construction is not a good idea to obtain a practical code. So in channel coding theory, people are concerned about finding codes that are practical, and in real practice, all codes are linear because these codes have efficient encoding and decoding, in terms of computation and storage. And channel coding has been widely used in the many applications, including home entertaining systems like CD, DVD, computer storage systems, CD-ROM, hard disk, floppy disk, magnetic tape, and I also want to add an SSD to it. In computer communications, wireless communication, deep space communication, and the famous codes that are used in practice are Hamming code, Reed-Solomon code, BCH code, turbo code, LDPC code, and Polo codes. In particular, turbo code, LDPC code, and Polo codes are almost capacity achieving, and they are practical codes. So this brings me to the end of my lecture today. Yeah, thank you for your attention.
Okay.
Yes, I can take some questions.
So maybe by the time others come up with some question, Raymond, I had a question about yesterday, something you said. You showed this jointly typical set, the particular structure about them in a rectangular this thing, which also came up today, and you mentioned that this is connected to group theory. Maybe for some particular distribution, this has a group structure or something. I am just curious.
Okay, now it turns out that there's a deep connection between entropy and groups. Okay? Specifically, they share the same set of inequalities, meaning that inequalities that constrains entropy function corresponds to a set of inequalities constraining the order of finite group and its subgroups.
Okay.
But there's another story which I cannot explain at this point. We can talk about this offline, or you can take a look at chapter 16 of my book.
Okay.
And it's mainly the results mainly coming from Terence Chan, the advisor of Strategic, when he was my graduate student.
Okay. Sure. Thanks.
Is there any chat? Let's see.
So there's nothing in the chat yet. So yeah, if anyone has any question, please feel free to either unmute yourself or type in the chat.
Well, I mean, the time is really short. I mean, 2 hours talking about channel coding theory is quite challenging. I hope I don't expect the students can get all the fine details, but I hope that they can get a high level understanding of the ideas behind the channel coding theorem and develop some appreciation of it.
Yeah. This I think covers the main important results, but there are many other things surrounding it, which I'm sure they can follow up from the book.
Or from the MOC that I produced earlier, which is available online.
Right.
What's the significance of network coding? Okay, there's a. Oh, we're going to talk about it on Thursday.
Yeah, so you nicely walk us through the whole, whole details very well, step by step. So that was very interesting. And I found that interpretation very interesting, that Markov chain and how H of W is mutual information between X and Y, if we want to make sure that if we want to transmit reliably. So that explains really well. Yeah.
I was just trying to find a way that I can see the solution. Without seeing the solution, you cannot even prove it. But I'm sure that Shannon didn't go through this route, but he has some other ways.
So some student had some query regarding video. So we'll upload the videos. I mean, I'll as soon as I get the access to all videos, then we'll process them and make sure that put them on a YouTube video, YouTube channel for this summer school.